In this video, we're going to discuss ionic solubility, trace solubility, or more specifically, the solubility product. There are many ionic compounds that are sparingly soluble. Often when we say something is insoluble, we just mean that it isn't soluble to a reasonable amount for us to work with. But almost everything is soluble to some amount. As long as it's ionic and can break into smaller components, some amount of them will separate. Now, this is different for things that are continual matrices, like, say, plastics. They don't tend to really dissolve if they're one really long mass of a single molecule. They may break down over time. That's part of our problem in the oceans. But here we're talking about ionic compounds that can be dissolved by water. They just don't necessarily do it very well. So we have some chemical, X, there's W of them, and Y, there's Z of them. So this is some solid. This could be something like calcium hydroxide. But that is, there's a cation and an anion, and there's some number of the two of them. Well, that solid, if you put it in water, can begin to dissolve. You'll end up with that number of the X ions, and it's going to be positive to some amount. They're going to be aqueous. And you end up with Z number of the anions to some charge, and they're going to be dissolved. How does this work for calcium hydroxide? Well, the solid, if you put it in water, becomes a calcium 2 plus aqueous and 2-hydroxide aqueous. So we're just dissolving things. But these are equilibriums. When you are low solubility, a good chunk of your material never fully dissolves. So you can have a beaker, has water, you go and you put in a bunch of a solid, and very slowly over time, a little bit of it will dissolve. Those little bits will bounce around and eventually hit the solid mass and kind of stick back onto it. And over time, a few bits will escape and drift around to eventually stick back into the solid. These are in equilibrium. When you don't have a material that's readily soluble, then you get an equilibrium between the dissolved ion components and the solid material. Well, in an equilibrium, the K of that equilibrium is going to equal the products. In this case, let's go with our example calcium here. Calcium 2 plus to the first power, and hydroxide, OH minus, to the second power. Remember, your exponent in your equilibrium expression is whatever the coefficient in the balanced reaction is. Well, all that's going to be over our calcium hydroxide. Well, as we give different situations, K values, different names, when we're talking about sparingly soluble salts, this is KSP. Equilibrium of the solubility product. One thing that happens here, well, we got to think about a solid for a minute. Let's imagine I have a big block of calcium hydroxide. In this case, I'm going to say it's 4 size units large, so let's just say it's 4 milliliters. And each of those is X grams. So this is 4X grams. So it's X grams per milliliter. Well, if we were to get rid of one of them, it dissolves and goes away. Well, now I'm left with 3 of that weight, but only 3 milliliters. This still equals just X per 1 milliliter. If you get rid of 2 of them, you'll have 2 of the weight units over 2 of my volumes. If you get rid of all but the last one, you'll have 1 of my weight units over 1 of the volumes. The concentration of a solid doesn't change as it dissolves. You lose some material, but they leave from the volume they used to occupy. So your volume and your mass go down proportionately at the same rate. Get rid of half your volume of solid, you've lost half your mass. But that means the ratio of the two is still the same for what's left. Solids don't change their concentration. They're constant, which means this factors out similarly to the way water gets factored out a lot in our weak acid base calculations. If the concentration isn't altering, it just ends up being multiplied up into the constant. So really our Ksp value, our equilibrium constant for this solid dissolving into solution, is just based on the ions. And this will be true for every time you have a sparingly soluble solid dissolving into solution. The solid will cancel out, and really our equilibrium is just dependent on the concentration of the dissolved ions. They're the things that need to come back together to form the solid. How long it takes them to find each other is based on how concentrated the solution is, how many of them there are to run into each other. Well, what are Ksp values here? Let's do an example. The Ksp here for calcium hydroxide is actually 6.5 times 10 to the minus 6. We're going to use that to find pH. So calcium hydroxide isn't terribly soluble. If you scoop a bunch of it and throw it into a container of water and let it start to dissolve, some will, but a lot of that solid is just going to sit at the bottom. And so it's going to dissolve until the maximum amount does, until it reaches equilibrium. And we can figure out how much that will be. And since hydroxide is created when that happens, is released from the solid and floats in solution, well, that's going to set our pH. We're going to have a lot of hydroxide around. Or, well, some amount of hydroxide. Let's figure out how much. Well, our Ksp has to equal the calcium 2 plus and the OH minus squared. And we know that the Ksp is 6.5 times 10 to the minus 6. That's got to equal my calcium 2 plus, my hydroxide squared. Well, how much of those are there going to be? Originally, none. So you can kind of imagine the table. Hey, I'm making some calcium 2 plus and I'm making 2 hydroxides. Initially, we're unconcerned about the calcium hydroxide itself, but we start with none of our products. And then there's going to be some change, and we're going to not be concerned about the solid because its concentration isn't changing, but we are going to gain some amount of calcium, and we're going to gain twice that amount of hydroxide. Remember, it's OH2 in the formula for calcium hydroxide, so for every calcium that gets freed, 2 hydroxides get freed up in solution. Eventually reach equilibrium, and so I'm going to have X amount of calcium ions, but I'm going to have twice that amount of hydroxide. Our Ksp is 6.5 times 10 to the minus 6, which has to be equal to X times 2X squared. Well, that squares on the outside. Remember, you have to do it to both parts. So really, this becomes X 4x squared, so 2 squared and x squared. All that has to equal 6.5 times 10 to the minus 6. Times those together, 4x to the third must equal 6.5 times 10 to the minus 6. I can divide by 4 on both sides. I will get 1.625 times 10 to the minus 6 equals x to the third. Take the third root of both sides, and my x must equal 0.011757. A few extra sig figs here, but basically 0.012. Well, that's what x equaled, and our hydroxide concentration was 2x. So twice that, 0.0235, must equal our hydroxide concentration. So we can take the negative log. Our POH is going to be 1.6287. So 14 minus the POH would equal our pH, which is 12.37. If you put calcium hydroxide solid into a container of water and just let it equilibrate, dissolve as much as it will, it'll successfully dissolve until 12.37 is the pH. At that point, you'll have so much calcium hydroxide in solution that they will recombine to form the solid as fast as the solid is dissolving. So it doesn't matter how much calcium hydroxide solid you pour into that container, it will not go above this when it is dissolving. It'll have reached equilibrium here at 12.37 pH. This is the idea of calculations using KSP. It's still in equilibrium. We're reorganizing to set everything equal to one variable and solve for that variable. Just introducing a new K value, this one specifically for the solubility product of sparingly soluble salts.